In this lecture, we're going to go through at least part of Chapter 6 and give you an introduction to eigenvalue and time-dependent problems. We're going to particularly first start out with first-order problems, things such as thermal transport, and then we'll go to hyperbolic equations that characterize things such as axial motion of a bar, or wave propagation. This could also mean electromagnetic waves. We'll primarily focus on structural vibration waves. So again, physics of interest are fluid and thermal problems. We'll look at the homogeneous part of the transients, and for structures we're interested in vibrating mode shapes. So one example is, say you have a plate, and if you excite the plate at its first mode, you'll typically see one large shape change, like a dome shape if you're considering a plate. The second one will usually be of higher order, and we'll keep going higher order. We'll do a few examples to illustrate this point in more detail in class and later with finite element, but for now let's set up the governing equations and show you how you can do this numerically. So remember, eigenvalue problems take on a form that looks like this. So lambda is your eigenvalues, u is your eigenvectors. So these are our unknowns. We want to solve for lambda, where a and b are dependent on the physics of the problem. So the two examples are parabolic equations, here particularly for 1D heat transfer problems. So we're talking about U would be a temperature, cross-section area of a bar, thermal conductivity, you have some type of heat transfer, and here's your first order rate effect. So we're just talking about an energy balance equation here. Second one is for mechanics, this is a force balance. You have your stress-strain behavior, or really this is divergence of a stress. You may have a distributed load, and this basically is distributed force. This is an internal force due to changes in stress, and that has to balance with acceleration times mass. So this is a density, a cross-section area, and your acceleration. Alright, so finite element formulation for heat transfer problems. So let's take this heat transfer case. I'm not going to go back into all the details on how to extract lambda from this ODE, but remember there are solutions for u that are functions of exponentials. So you could write this as a set of exponentials in time. So you'd have e of negative lambda t. So you take a time derivative, you're going to get a lambda here, and then u would also be a function of space. So you have these additional derivatives or functions of u in space. And one thing we've done is assume separation of variables. So we take u to be of this form. So that restricts certain physical phenomenon. Particularly, we will normally linearize this problem around an operating point. So you simplify the modal analysis, and that becomes apparent here where we have heat transfer. We're saying that these are linear, or these are constant coefficients, or things like thermal conductivity geometry. This affects your convection on the surface and your specific heat, density, and area. Similar for bars. You can solve these problems for bars too. This is elastic modulus, cross-section area. C would be 0 in that case, and C naught is your density times your area. Alright, so remember, in the finite element problem, we're going to approximate our true solution